All right, thank you. So, yeah, my name is Guillaume Henderson. I'm a PhD student at CMET at Ghent University, and I will be talking a bit more about membrane electrolysis and lithium extraction and mainly conversion. Good. So, this is an overview of like several sources of lithium in. One second, I'll just show my pointer. Yes. So of lithium sources all over the world. So we have the clays, natural brines in South America, spodumene rocks in Australia, geothermal brines in Europe, and there are quite some more which are not even listed here. And each of these primary or secondary resources, they all have their own specific extraction processes, which are quite different. But at the same time, a lot of these sources, they have a couple of things or one more specific thing in common. And it is that they start from a very low concentration of lithium, and they all want to purify this lithium and bring it up to higher concentrations. And then finally do a conversion step to battery grade lithium carbonate or lithium hydroxide. And it's especially in this conversion step from lithium chloride to or lithium sulfate to lithium hydroxide and lithium carbonate that we're going to talk about today. So very commonly these days, doesn't matter which type of source you have, there will always be a chemical precipitation step involved where you're going to convert your lithium chloride or your lithium sulfate into lithium carbonate. And how do they do that? Well, very commonly, it's done by the addition of sodium carbonate. That's because sodium carbonate is super soluble, and lithium carbonate, especially at higher temperatures, is much less. And in this way, you can selectively crystallize your lithium carbonate out of the solution. You can also go for lithium hydroxide by the addition of calcium hydroxide. But as you see, there are a couple of drawbacks. Well, first of all, there is quite some waste that's being generated because you're adding chemicals and you're not recovering all the chemicals. So you need to do, well, either you landfill everything, but especially with more stringent legislation that's being implemented, it's harder and harder to just simply dispose or landfill everything. So we also need to treat these waste streams, which is also costing money. And secondly, there is also a significant amount of CO2 emissions involved with this processing. And it's said that up to 10% of the total cathode production CO2 emissions are coming from the lithium refining, or in total 2 to 3% of the battery CO2 emissions. Now, an alternative technology is membrane electrolysis, and instead of using chemicals, actually the only thing we will need here is, as an operational cost, is electricity. And in theory, if you're using green electricity, you can eliminate the CO2 emissions, and at the same time, you can valorize byproducts, um, for example, acids or other chemical compounds, instead of just landfilling them. So how does this electrochemical cell work? Well, let's take the chloralkali electrochemical cell as an example. The example which is used these days for the production of sodium hydroxide and chlorine gas, which can be used in plastic production like PVC, for example. Now, you have your two electrodes. You're going to apply a current. You will have an oxidation reaction taking place at your anode, and you will have a reduction taking place at your cathode. The anode, here you will have a gas formation, for example, chlorine gas in this case, and you will be producing, you will just be producing chlorine gas. And at the cathode, you will be producing hydrogen gas, and you will also be producing hydroxides. So at the same time, you will have hydroxide formation in the cathode, so you will have a difference in pH between the catholyte and anolyte, especially if you are going to separate these two compartments with a membrane. A cation exchange membrane, in this case, will enable the migration of cations and will block all migration of anions. Now, when there is a redox reaction taking place, there will be a flow from electrons from your anode to your cathode. So this cathode will become negatively charged, but you cannot just simply have a negatively charged solution this has to be balanced. So for every electron that migrates to your cathode, you will have a cation migrating over your membrane, in this case, going to the catholyte. And this is why you can then concentrate sodium hydroxide in the catholyte solution and reject all chloride ions and have a pure solution here. Good. The first application or possible configuration of an electrochemical system to use in the lithium refining business is electrodialysis. Here, in this case, you're not just going to have one membrane and two electrodes, but you're going to have, as you see, a lot of different membranes, a cation and anion exchange membranes that are alternated, and you will have one anode and one cathode. And the amount of membranes in between these two electrodes can be sometimes up to more than 100 membranes. So what is this being used for? You're not going to generate hydroxides or acids, but you're going to concentrate your initial feed. Because very typically, your lithium chloride can be in just maybe 1 or 2 grams per liter, which is not super beneficial if you want to do either chemical precipitation or conversion to lithium hydroxide. So therefore, you wanted to first to concentrate this feed. And you're going to insert it into all the different compartments, and you're going to apply a current. And all the positively charged ions, so lithium, they will migrate towards the cathode in this direction. So, but they will migrate over the cation exchange membranes, but they will be blocked by the anion exchange membranes. So what you will see, this is wrong here, an error, sorry. But what you will see in this one here is that the lithium ones, they will be blocked by the anion exchange membrane. And the same will be happening for the chloride ions, which will be blocked by the cation exchange membrane. And thus they will be concentrated in certain compartments, in this case, the blue compartments. And thus you have a more concentrated stream. And here you can concentrate them up to 10, 15 grams per liter easily. Good. Another conversion another configuration is this 2-compartment electrochemical cell, which you can use for the conversion of lithium chloride into lithium hydroxide. This is in fact super similar as what I described previously with the chloralkali configuration to produce sodium hydroxide. And what's very particular in this configuration is that you will be producing chlorine gas. Now, why chlorine gas and you will not be splitting water and forming oxygen? Well, that's because if you look in the standard reduction potential table, what you will see is that chlorine gas evolution and oxygen evolution are super close to each other in this table. So that means that energetically both could be happening. But in these type of configurations, what you will do is you will take a ruthenium mixed metal oxide anode, which is a titanium electrode coated with a ruthenium layer, and this ruthenium layer is super selective towards the oxidation of chloride into chlorine gas. Now, what's the benefit of that? That you will be producing chlorine gas that will leave your solution, and at the same time, you will not be forming any protons. So you will only have lithium in your solution, and then lithium can go over your membrane, and you will have a pure and super efficient process to produce lithium hydroxide. Now, if you want to use this type of process or electrochemical cell, you will need a cation exchange membrane, and it's very important to choose the right membrane because the right membrane will determine the performance of the overall system heavily. Now, what are you going to look for these type of membranes? First of all, chemical resistance. As you see, there is chlorine gas that's being produced. Chlorine gas is a super corrosive element, so your membrane has to be resistant to chlorine gas. And typically, these type of membranes are fluorinated membranes because the bond between the carbon atom and the fluor atom is one of the strongest bonds that you can find. Second, the membrane resistance, that is the resistance of the membrane, and the higher the resistance of the membrane, the higher your overall cell voltage will be, and thus the more electricity you will need because you have a higher resistance. So you want the resistance of the membrane to be as low as possible to have a low resistance and thus energy consumption. And thirdly, you will also want a high transport number, because a high transport number means that you can cross a lot of lithium ions through your membrane. And then lastly, of course, the cost is very important. You want your membranes to be as cheap as possible. Now, what is the most important factor also is that your membrane is able to block very efficiently hydroxides, because you have an anode that attracts the negatively charged hydroxides, and they will also want to go over your cation exchange membrane because they're attracted by the anode. So you want your membrane that will only enable lithium migration and block hydroxides as much as possible. And for that, what you will be looking for is, or what is very typically used, is a bilayered membrane. And those are very precious but very good membranes for this type of application. And they typically exist of two layers. First, you have a layer of more standardized polymer, fluorinated polymer with sulfonic functional groups. And then you have a small layer with carboxylic acid functional groups. And it's especially this layer here, the carboxylic groups, that are very efficient in blocking these hydroxide ions to migrate over your membrane back to the anode. And that is the reason also why in sodium hydroxide production, they can go up to 8 moles per liter in the catholyte of sodium hydroxide, which is very, very high compared to a lot of other applications. Good, but then what if you don't have a lithium chloride source, but you have a, or stream, you have a lithium sulfate stream? Well, if you would use the same configuration, where you have a 2-compartment electrochemical cell, you would not be producing chlorine gas because there is no chloride in your stream. There is only sulfate. So you will be producing oxygen and protons. Now, these protons, they will acidify this anolyte solution. And at the same time, there will be a lot of extra positively charged ions present next to your lithium. So what will happen is that the protons, they will also start to migrate towards the catholyte, and they will not only compete with your lithium ions, but they will also neutralize the hydroxides that are being produced at the cathode. So this is really not what you want, and therefore it's important that you keep the pH of your lithium sulfate solution above 2, otherwise you will have proton competition. Now, if you want to treat your lithium sulfate solution then with an electrochemical cell, you would need a 3-compartment electrochemical cell where you include an anion exchange membrane. What will happen then is that your sulfate ions, they will go to your anolyte and they will accumulate in this compartment, while the protons that are being formed at the anode, they will be blocked by the anion exchange membrane. And if you are looking into concentrating this sulfuric acid as well, which can be beneficial because it can be used, for example, in leaching steps with the mining of mineral rocks, then you will be typically looking at 3 specific characteristics in your membrane. That is all to block the protons from migrating back. So first of all, protons, they are very, they are surrounded by a lot of water. So, and what researchers have seen is that every time that the proton, or a factor that influences the proton migration over the anion exchange membrane towards the cathode is the water content of your anion exchange membrane. The more water is present in your anion exchange membrane, the more protons will be going over your membrane as an inefficiency. So therefore, what you're going to do is you're going to add a lot of hydrophobic groups into your membrane in order to reduce the water content, and in this way, you hope to exclude the protons. But of course, you can never put too much hydrophobic groups in there, because what will happen, your resistance of your membrane will become too high. So therefore, you will also not want to do it too much. And the second thing you can do is increase the charge of your membrane and thus increase the ion exchange capacity. But what will happen then is that, so what you hope to do is that you will block by the extra charge, the positively charged protons. But what will happen is you will attract more sulfate ions, which contain water around them. So you will increase the water content also. So you really will need to make a trade-off between either between hydrophobic groups, cross-linking, and ion exchange capacity of your membrane. But of course, if you don't want sulfuric acid, there are other options. For example, instead of producing an acidic solution, you will insert a buffer solution in your anode. For example, ammonium. This ammonium then, with the protons generated at the anode and the sulfates migrating into this compartment, will form ammonium sulfate, which then can be recovered as a compound and also valorized. And in this case, you don't need these specific membranes with proton locking ability, but you can just use a more low-cost membrane, which has a lower voltage and a high ion exchange capacity, and maybe are also a bit cheaper. So, but of course, this all depends on the availability of the waste streams available or the compounds that you want to valorize or have in your stream on site. And then a next type of electrochemical system is an electrochemical cell with a bipolar membrane. So we've seen previously in every configuration that we had an anode and a cathode, which were generating gases. We were generating oxygen gas or chlorine gas at the anode and hydrogen gas at the cathode. Now, the bipolar membrane will actually take over the function of the electrodes, and you will not have the hydrogen gas and oxygen gas formation in this membrane, but what will happen is water diffuses into this membrane, and then here you will have a dissociation of water into a proton and a hydroxide. And then this proton and this hydroxide, they will migrate out of your membrane again, and then you will have an alkaline solution here where you can form lithium hydroxide, and you will have an acidic solution where you can form sulfuric acid. The bipolar membrane itself is actually nothing more than just an anion and a cation exchange membrane glued together, and together they have these properties. Now, what's the benefit of this membrane is that there is no gas production. Overall, there will be a lower cell voltage and thus a lower energy consumption for your whole system in order to produce lithium hydroxide, which is of course what you want because electricity is your main operational cost. Now, there are still some drawbacks with this technology, and that is mainly in the bipolar membrane. That, well, first of all, these membranes, they're still quite expensive. So we really need to work on the cost, lower the cost, and also the maintenance of these membranes is still quite high. And secondly, the purity of this lithium hydroxide that you obtain here is going to be lower compared to the 3-compartment and 2-compartment systems that we have seen before, because you have an ion leakage and you have sulfates accumulating in this compartment, and they're attracted by the anode. So they want to migrate in this way, but a membrane is never 100% perfect. And what you see is that typically you have roughly 5% of impurities that go into this direction, meaning that your lithium hydroxide purity reduces from 99.5 to 95, 96%. And then you will need further purification steps because 95% is not high enough for battery production. And then the last drawback is that especially the anion exchange side of the bipolar membrane is still not very resistant to high base concentrations, and therefore they also need to further improve to have a widespread implementation into this sector. And then the last configuration, which I'm going to talk about, is the gas diffusion electrode. And that is, in fact, again, the 3-compartment system that we have seen before with an anion and a cation exchange membrane. But what you will do is you will take the oxygen from the anode, and instead of just letting it go, you're going to reinsert it into the catholyte, and you're going to contact it with the cathode. Now, what happens is that you will not be forming any hydrogen gas at the cathode, but you will have another reaction taking place. And instead of the first reaction here, you will have the second reaction. So water and oxygen, they will form only hydroxides. What is the benefit of that? Is that the overall cell potential is lower of your gas diffusion electrode compared to the regular 3-compartment electrode system, where you're going to form hydrogen. And thus, if the cell potential is lower, what you will have is a lower energy consumption, less electricity consumption, and thus a cheaper process to convert your lithium into lithium hydroxide. Good. That was it. Thank you for your attention. And if there are any questions, I'm happy to answer them.